Volcanic eruptions do contribute to climate diversity, and you see why from this presentation. I will introduce how volcanic eruptions affect climate. Then I'll talk about recent examples of volcanic eruptions and a number of influences, including ocean heat waves, extreme weather events, the long and strong 2014 to 2016 ENSO, polar sea ice changes, and the 1995 acceleration in sea level rise, which is seen in many parts of the world. Then I'll draw up some conclusions. I'll start off with definitions of climate change. The United Nations definition has some problems because they assume they know what is directly due to human activity. The IPCC, which is an organization funded by the United Nations, has a slightly better definition based on statistics, usually decades or even longer. But because of the pause in temperature rise, all weather changes are now included in climate change. I like the last definition, a product of astronomical forcing, including solar variability and the interaction of the Earth systems. And this is the part most difficult. The air, atmosphere, water, hydrosphere, the plants, living things, biosphere, the frozen earth, cryosphere, the soil, pedosphere, and then the lithosphere, including volcanoes. So it's a lot more complicated than we think. It's not just CO2 from fossil fuel. The order of importance in driving climate, most important first order is the sun, and that's what is called astronomical forcing, the planets. What is truly global climate change are the interglacial glacial cycles, the ice ages, and then the milder periods. The rest are mostly regional change, including monsoons, seasons, even daily changes. Second order importance are the geothermal heat from the lithosphere, and then from below that, the magma. This is what is called plate climatology. And third order are the human-induced changes, including heat generation, water cycle changes, and greenhouse gases. And some people are thinking that CO2 will overtake the sun to become first order. Is this likely? I'll start off with classification of volcanic eruptions. They can be divided into three main types: subaerial or terrestrial, that means on land, switches on hot air followed by cooling, causing a number of influences, which I've listed here. The second main type are the submarine volcanoes on the seafloor, and this causes the seawater to be heated up at the surface because hot water is lower in density, so it forms ocean warming regionally. And of course, there's a mixed eruption. Submarine volcanoes may eventually build to form a new island, and after the island was formed, it becomes subaerial. For example, the Tonga eruption earlier this year from December 2022 to January 2023. The subaerial volcano model is summarized here. The volcano releases ash and aerosols, and this reduces solar radiation, leading to cooling. Warm air also stores more moisture, so water vapor distribution, air pressure changes. This is a picture of the El Chichon volcano in Mexico in 1982. It was shown by satellite to circle the globe in 21 days. And Hong Kong had its second wettest year on record since 1884 because of the influence of the volcanic clouds. Eruption changes normal air circulation, creates clouds, destroys ozone, releases gases such as sulfur dioxide, which is of great importance in solar radiation impact. Cool air stores less moisture, and the impact lasts longer if the volcanic eruption is larger, based on the volume of material released into the atmosphere. The volcanic explosivity index is used to quantify the size of volcanic eruption on land. By the bigger the volume, you see the big red circle is a scale of 8. The Yellowstone eruption 600,000 years ago was thought to be of this scale. The biggest eruption in the last 100 years or so is Pinatubo in 1991, and it has a scale of about 5 to 6. So this is the measure based on explosiveness of the volcanic eruption. But in terms of influences on climate, if VEI is 2, already we can see regional impacts on weather detectable. We are fortunate since the late 1970s to have satellites to measure volcanic cloud, to track how they are being distributed around the globe. So this is NASA's A-train called Calliope. So we can do profiling of volcanic clouds. So this is what makes flying a lot safer. If there's large quantities of ash from volcanic eruptions in the atmosphere, it can cause jet engines to stall, causing the planes to crash. How does a volcanic cloud influence the atmosphere? The upper part is called the stratosphere. Normally, the jet stream get interfered with because of the height of the volcanic cloud. Now, the Tonga eruption earlier this year reached a height of 58 kilometers. Typhoon clouds reach 12 kilometers. So it's overwhelmed by these volcanic eruptions changing the circulation. It caused the jet stream to change its course, causing it to meander. Volcanic eruptions also brings a lot of water vapor, creating atmospheric rivers in the sky. And this is a picture of one over the west coast of Canada. Because it comes from Hawaii, it's called the Pineapple Express. Of course, we also have submarine volcanoes. 3 examples that I have studied are shown here. One in the North Atlantic, El Hierro, in the Canary Islands. Tonga eruption in 2014 to 2015. So this is an earlier eruption than the one this year. And then one south of Japan called Nishinoshima, 940 kilometers south of Tokyo. And this is a long-lasting submarine eruption of almost 2.5 years in the North Pacific. The impacts of these submarine eruptions are that it creates warm surface ocean water, mistaken for global warming regionally. Pressure changes, surface wind changes, sea level changes due to the heating up of the water, you have thermal expansion, ocean circulation changes, and even polar sea ice changes, which I'll show later onwards. So basically, we are talking about regional ocean warming. Basaltic magmas are much hotter, so it has a temperature of about 1,200 degrees Celsius. Statistics on submarine volcanoes are summarized in this table. Approximately 1 million, and 75,000 are rising from the seabed by about 1 kilometer, still submerged by the present sea level. Magma output is enormous, 75%, and we have about 5,000 submarine volcanoes which are active. Basaltic magmas are obviously hotter than acidic magma, but acidic magma is much more explosive. So these submarine volcanoes releases geothermal heat during eruptions, changing the normal oceanic circulation and atmospheric circulation. So the ocean warming may lead to ecological changes mistaken for global warming impacts. We are fortunate that from year 2000 onwards, we have started to have oceanic floats measuring temperature and salinity profiles in the oceans. There are now more than 4,000 of these floats, so they are a good way of detecting hot water rising to the surface from submarine volcanic eruptions. So this is a subject that at least Earth scientists should be interested in looking at. These floats are maintained by different countries, mostly the United States, but China also are involved, as well as many other countries. Now, this is a table which is a bit long and difficult to read, but what I've tried to do is, from volcanic eruptions since the year 2010, listed the major climatic impacts. You won't be able to read through it, but this PowerPoint will be available to you later onwards, and you can read through it. It's a combination of terrestrial eruptions, submarine eruptions, and mixed volcanic eruptions. The location of the volcanoes are shown in the second column, and the timing of the eruption and the climatic impacts that we have found out are shown in the last column. And these climatic impacts included polar sea ice changes, which I'll show in more detail later. Hot seawater patches, the most famous is the North Pacific blob as a result of the eruption south of Tokyo, Nishinoshima. Because it's a long-lasting eruption of 2.5 years. The hot seawater lasted much longer and the impact was much greater. Shorter submarine eruptions will have shorter impacts. It may also lead to coral bleaching, also mistaken for global warming. Now, this Iceland eruption, which is difficult to pronounce for most people, I've simplified here to call it E15, 15 letters after the letter E. So this is actually the name of the eruption. It erupted on 14th of April 2010, and it caused major disruption of international flights from Europe to North America. So the brown is actually the cloud, the volcanic clouds. This is the particulates from the volcanic eruption or tephra that may cause the jet engines to fail. People don't realize that this has major impact on extreme rainfall. The weather chart based on satellite analysis is shown here on the 29th of April, 2 weeks after the eruption. And you can see from Iceland, which is located here, a succession of occluded fronts, one after another, penetrating deep into the continental interiors of Europe and Central Asia. And one country along its path, Slovakia, has its wettest year on record since 1818. This is actually the station, Herbanova. The red graph is the temperature, the blue is the rainfall. And you can see that as the rainfall goes to a record high in 2010, it led to cooling of the temperature. So the temperature dropped, showing that the rainfall actually lead to cooling. So this is how moisture is able to penetrate deep into the continental areas. Without volcanic eruptions, this cannot take place. The submarine eruption of El Hierro in the Canary Islands in 2011 to 2012, which erupted for 6 months, led to some notable extreme weather events. The one that affected New York, causing 147 fatalities, is Hurricane Sandy. Estimated damage, US dollars 65 billion. And then in the United Kingdom, during 2012, you have the wettest summer in 100 years and the wettest week in the last 50 years in November. So this is a chart of the floods based on treats. So you can see that southwest England around Somerset was severely impacted by flooding that particular year. And this is explained by the warm North Atlantic Ocean, successive frontal activity storm bringing heavy rain to the United Kingdom. In 2014 to 2016, we have one of the longest and strongest ENSO on record. So this is the appearance of hot seawater off the coast of South America. But normally ENSO occurs around Christmas time, but this event is totally different. And I'll go to explain why from these sea surface temperature maps from NOAA. The volcanic eruptions playing a part in this ENSO event, El Niño, are summarized in this table. July 2012, a lot of people don't know this, north of New Zealand, there's a submarine volcano called Hefre. And this was the largest deep water silicic eruption of the past century. The pumice raft floating to the surface has a total area of 400 square kilometers. It has 14 vents, and the water depth is from 900 to 1,220 meters. Then in 2013, we have this Nishinoshima eruption south of Tokyo, and this lasted for almost 2.5 years. After a new island was created, it becomes subaerial. 2014 to 2015, Hunga Tonga erupted. So it has erupted 3 times, not just this year. Previously in 2014, 2015, and then another time later onwards. Exil Seamount is in North Pacific Ocean. Wolf Volcano is in Galapagos, and this is a volcano on an island with hot lava flow flowing into the Pacific Ocean, heating up the seawater. Hawaii, Killer Whale, was also active. Again, you have basaltic lava flowing into the Pacific Ocean. So you have multiple heat sources to heat up the seawater in the Pacific Ocean. This is a photo from the air of Nishinoshima as it created a new volcanic island. But lava flow continued, and you can see the island building up. So this lasted for almost 2.5 years, heating up the North Pacific Ocean. We have these NOAA sea surface seawater anomaly maps. Nishinoshima is shown here in this red triangle. And because of the circulation in the North Pacific, it forms this hot surface water patch of enormous size close to the coast of Alaska and Seattle and so on. So this is due to geothermal heat released from the submarine eruption and the change in ocean circulation and atmospheric circulation. In the North Pacific, we have these gyres, and basically the hot water built up in these gyres. You can see off the coast of Alaska, off the coast of British Columbia, off the coast of Southern California, Mexico, and so on. So it evolved and separated into three parts. So the heated water brings new ecology to these areas, even though it's just for 2 or 3 years. National Geographic, in fact, showcased this ecological damage and caused it a giant patch of warm water known as the blob shocks the Pacific in what some fear is a preview of our future oceans. But this is strictly a regional warming event due to Nishinoshima. So you have mass mortality of many marine life forms resulting from it. Sea surface temperature anomalies after multiple eruptions ended in June 2015 is shown here. So the Hunger eruption is shown in this red triangle. Hawaii, you have coral bleaching. The axial seamount, which is off the coast of Seattle, erupted from April to May 2015, and then Wolf eruption from May to June 2015 at the location where normally you have the El Nino, hot seawater. But you can see the timing is not Christmas time by any means. It is in June, July. Establishment of the very strong ENSO was during August, the end of August. You can see this heated water spreading across the normal region. But this is quite different from previous ENSO event, as in that you can also see the hot water further north in the North Pacific Ocean. Measurement of seawater temperatures here enable us to compare the ENSO event in 1997 to 1998 to the current one, which is 2015 to 2016. And you can see the thickness of the heated water is much, much greater than during the 1997-1998. So you have to account for the differences, which is supported by observation records. This is based on the work of Zhang in 2017. Now, I've mentioned that there are impacts on Arctic sea ice as a result of these submarine eruptions, and this is shown in these charts. Normally, in the Northern Hemisphere, summer heating of the Arctic will lead to minimum sea ice in September. So I've shown here 2014, 2015, 2016 sea ice extent, which is the white area in these charts. Wintertime temperature dropped, so winter onset, so the sea ice expanded. Based on the measurement of sea ice from the National Sea Ice Organization in the United States, the lowest record of sea ice was in 2012. 2014, 2015, 2016, when Nishinoshima was erupted, you have more gradual decline, but not as low as 2012. This led to our explanation. We have discovered the connection with submarine eruption. 2012, with the record low sea ice, was due to the El Hierro eruption in the North Atlantic. Shrinkage of sea ice is much greater in the North Atlantic as compared to 2014 to 2016. Shrinkage is much greater in the Bering Strait area. So if I go back to the previous slide, you can see it. 2014, 2015, 2016, the sea ice extent has shrunk much further near the Bering Strait, consistent with the heat source from the North Pacific block. If the heat source is from the North Atlantic, you would see much smaller, much faster sea ice retreat in the North Atlantic Ocean. The final thing that I'm going to talk about as an example of volcanic influence is sea levels in Hong Kong. Hong Kong tide gauges measuring sea levels are shown on this chart. We have 6 tide gauges. One of them is no longer in use. This is Chimawan tide gauge. It was discontinued. So we still have 6 tide gauges. The longest record in terms of tide gauge measurement is from North Point Quarry Bay. But why 2 locations? Because they have moved the tide gauge in 1986 from North Point to Quarry Bay due to the construction of the Eastern Corridor. So the engineers were concerned that it will affect the measurement, so they changed the location. Hong Kong Observatory was responsible for this record. What they have done is to draw a mean graph for this period of monitoring from 1954 all the way to the present. So these are annual mean in sea level. So they just took a mean graph line to represent the trend of sea level rise. And they come to the conclusion it's rising at a rate of 32 millimeters per decade every 10 years. But what have they missed out on this record? Now you can see that the record is not straightforward. It has in fact gone down a little bit, gone up very fast over this period from 1990 to 1999. Then the rise has disappeared. So if you look at the record in more detail, you can see all this. If you have good memory, you know the driest year on record is 1963. And you can actually see a low sea level point during the driest year. Why driest years are lower in sea level, you may ask? High pressure, little rainfall. The wettest year on record is 1997, based on the record of rainfall from 1884. So has this also got an influence on this rising sea level in this period, 1991 to 1999? More water discharge from the River Pearl into the Pearl River estuary may be responsible. More rainfall means lower pressure. Low pressure means higher sea level. So this seems to be consistent. So you can have other explanations coming in. But I think all of you can also see these arrows. 1959 to 1991, you have a 32-year pause in sea level rise. The highest point was 1959. Sea level has continued to drop. But then we have sudden acceleration from 1991 to 1999 in this location from Victoria Harbour, one location in Hong Kong only, a rise of 26 centimeter, which we can correct based on comparison to Tai Po Kau Station as absolutely not more than 17 centimeters. Then we have another pause in sea level rise from 1999 all the way to the present day, 23 years. So if CO2 is driving global warming, sea level rise, we don't see this in our record, right? The station have been moved, but they have shown it as a continuous record. So our conclusion in terms of sea level can be summarized in this table. There may be cyclic changes in sea levels that we don't know about. We all know the Chinese calendar has 60-year cycles, what is called the Atlantic multi-decadal oscillation. Can we see this? Crustal stability through loading and unloading, through tectonic movement, erosion, deposition. We are at the mouth of a delta. Sedimentation could cause crustal loading, causing it to subside. Rainfall effect, dry years, wet years has to be taken into account. And then the accelerated sea level rise of 17 centimeter. And this is best explained by a professor from Florida. What is called the inflection point in marine seismic activity, which is shown in the previous chart with Terito. This is due to thermal expansion of the seawater in the oceans, causing this dramatic rise. So it's a temporary effect, and it's a cyclic change that we can see. Then we have the man-made impact. Hong Kong is an urbanly developed city with many high-rise buildings. Loading of the crust, surely we have some isostatic adjustment taking place. Reclamations also, landfills and so on. So the record in Hong Kong with the 60-year cycles is summarized here. Our record is basically too short. We have measurements from 1954 all the way to the present. So the record we see seems to be consistent with these 62-year cycles of Knudsen. So it has gone down and gone up slightly, but has gone down again. So it seems to be consistent with these pauses that we have identified from the Victoria Harbour tide gauge. So to finish off, our main conclusions is shown here. Based on observation records, the selective volcanic eruptions studied and the climate variability found are consistent with the timing, which cannot be explained by other means. I think the other things I've already said just a summary, but this PowerPoint can be made available to everyone who wants to read it in more detail. So volcanic eruptions as a cause in both cooling and warming is underestimated. It's part of our dynamic Earth. And I'll close with one cartoon slide. by Joss in 2018. And what is interesting, to fit in with the theme of this meeting, volcanic eruptions are a natural geodiversity experiment for us to learn from. So it leads to climate diversity, which is much more important than tourism, I think, if you ask me. I think the recent past is the key to the future. Thank you for your attention.